on logarithmic equations. Okay, so basically, there's two things that we're going to be doing. One is solving exponential equations. Here's an example, number one, and solving logarithmic equations. Here's an example. Okay, so to solve, so let's focus on this one first, solving exponential equations. And I put all these formulas up here for reference. I would say that this is going to get used a lot, and then as well as any of these down here. And the other ones are going to get used some too. Okay. So anyways, to solve exponential equations, what you want to do is you want to isolate the exponential expression on one side and then take logarithms. Okay, so here's an example. Here I have a 2e to the x. E to the x is not isolated because there's that 2 there. So we divide both sides by 2, and that's going to give us e to the x equals 40. Okay, so now what I want to do now is take logarithms of both sides, and there's a number of different choices. If you have e to the x, then for sure you want to take the natural logarithm in this case here. Okay, so the natural logarithm of this is equal to the natural logarithm of 40. This, we're going to use this, the inverse properties of logarithms, in particular the natural logarithm. This is just going to be x. Okay, and there you go. That's the answer. Let me write that better. The natural logarithm, x is natural logarithm of 40. Wait a minute. Whoa, my division skills are not very good. 40 divided by 2 is 20. This is embarrassing. The first time I ever made any mistake in my life. There we go. Okay, so natural log of 20. Okay. So they also want you to like highlight that, and then yeah. Okay. Now it also says use a calculator to find an approximate value. And sometimes they're supposed to do that. Other times you're not supposed to. So anyways, natural log of 20. So let's go ahead and use a calculator to figure that out. So geogebra.org, we use that calculator. You can also use a handheld calculator. Log of 20. Make sure you put that in parentheses, and there it is, 2.9957, what is it, 3 decimal places? 2.996 would be the answer with two decimal places. Okay, so that's 2.996. This is from GeoGebra. Okay, let's do the number 2, and that's solving logarithmic equations. Okay, so what you want to do is you want to combine logs and isolate the logarithmic equation on one side. Okay, so here we have a log plus another log. We have a log over here. This is isolated on this side, but then there's 2 logarithms here. So what we're going to do is we're going to combine those together using this first property here. So those combine to give you log of 3 times that. So that's 3 times x minus 4, that's 3x minus 12. We'll just write it like that. Okay, so that's combining them together. This is actually an answer to the first part of the equation. Okay, now what you want to do is you want to exponentiate. Okay, so let me kind of just illustrate what that is. Exponentiate. This is a term that only I use. I don't know if everybody else uses it. But the idea here is that this is log base 10, right? So we start with 10 equals 10. And then we raise each side of the equation to we raise these 10s to each side of the equation. So this 10 gets raised to that side of the equation, to the left side. this thing gets raised to the right-hand side of the equation, like that. Okay, and then what we're going to do is we're going to use this property here, the inverse property of logarithms. So 10 to the log base 10 of 3x minus 12 is just 3x minus 12. And 10 to the log base 10 of x is just x. So that equation just becomes that. Okay, and then this is another answer to one of the questions. And then the last thing you want to do is subtract this x over here. So that's 2x. Bring that 12 to the right side, and there you go. Now, the answer is 6. Now, with this one, I did emphasize that you need to check your answers in the original equation. Sometimes you'll do things that could introduce extra solutions. Like, for example, if you combine logarithms together, sometimes the logarithm of this, sometimes this new equation will have solutions that the original equation did not have. Okay, that has to do with when these can potentially be negative and positive. But since that's always positive, and we combine this one with that one, and the 3 is always a positive number, then we're fine. So that's not going to introduce wrong solutions. And if this is negative, then this will be negative also. So we're okay in that case. We don't have to worry about it there. Okay, but we'll show you some cases where we do have to worry about it. Okay, let's go to number. Oh wait, so 6 was the answer. Okay, so let's go to number 3. More adventures in mathematics. So here we have an exponential equation, and this one though is not that bad. So 7 to the 3x minus 4 equals, okay, 1 over 7 is the same as 7 to the minus 1. Okay, so what we can do here is we can take the log base 7 of both sides. You could also do natural log or log base 10 if you wanted, but log base 7 works out really great because both sides, their exponential base is 7. Okay, and then so we're going to use this property here to reduce this down to 3x minus 4 on the left and negative 1 on the right. Okay, so add 4 to both sides. So 3x equals 3, so x equals 1, and that's the answer. So 1 will be the answer. Okay, now let's do this one here. Here, again, we're going to use this, we're going to, take log base 3 of both sides. And use this property here, and we just get x squared minus 4 equals 4 minus x squared. Let's see, add x squared to both sides, so you have 2x squared over here. Add 4 to both sides, so that becomes an 8. And you're going to get 2 and negative 2 as the answers. Okay, let's do this one here. Another exponential equation. And again, you're going to isolate this. So divide by 3. So you have e to the x is 7/3. And then, because this is the natural exponent, we will use the natural logarithm. So take the natural logarithm of both sides. And then we apply this property here. All this just becomes x. And that's the answer. So log of 7 over 3 is the answer. And then use GeoGebra. So we're going to put log of 7 over 3 in using GeoGebra. And it is 6 decimal places, so 0.84729 and that 7 gets rounded to an 8. So 0.847298. So 0.847298, because that last 7 right there gets rounded up to an 8. Okay, so this is from okay, let's look at number 6. So we have another exponential equation. So what you want to do here is, first of all, there's this 4 here. So let's divide everything by 4. And that eliminates that, right? So we just have 3 plus 5x to the 5 to the x plus 1 equals, and 100 divided by 4 is 25. And now it's not quite isolated yet. We have this 3 here, so subtract 3 from both sides. And 25 minus 3 is 22. Okay, so 5 to the x plus 1 equals 22. Okay, now you want to take logarithms of both sides. And here's where it gets a little bit more interesting, because you can go log base 5, but usually people are going to go the natural log. Okay, so let me show you what happens when you do natural log. Okay, so what happens here, and this is the key right here. This is the key. This x plus 1 goes down there, okay? Out in front. But put parentheses around it, though. So you get that, okay? And now what you want to do is, there's a couple ways you can do this. You can distribute this log 5 into here. That's perfectly fine. But because it multiplies the whole thing and there's no x's over here, then it's probably easier to, in this case, to divide both sides by log 5. Okay, so it's just a standard, we're solving for x. So I divided both sides by log 5. Now subtract 1 from both sides. And there's the answer right there. Wait, this is log 5. What am I doing? Okay, so log 22 over log 5 minus 1. We're supposed to use a calculator, so let's just run through GeoGebra really quickly. Okay, so I know it's a fraction, so I'll type the slash key first. So log of 22, use the arrow keys to get down there, log of 5. And then I'm going to subtract 1 from it. So 0.9, so 6 decimal places. That would be 0.92057, and this 2 gets rounded up to 3. So 0.920573 is going to be the answer there. $920,573. Okay, again, that's from GeoGebra. Okay, this next problem illustrates, by the way, we could have done log base 5, and it would have been a little bit easier, because this would be log base 5 of 22. That's what this would be, because you recognize that from the change of base formula. But when you get to problems like this, where you have a 3 and a 7 as your basis for exponentials, then that kind of then you can't really use that exploit anymore. So they're both exponents that are isolated, so that's great. So go ahead and just take the natural log off the bat. Okay, and then these are both going to go out in front, okay, in front of the equation. But when you do that, put parentheses around it, because otherwise you can get into trouble. Okay, now the problem here is you have an x there, and you also have an x there. So you can't just divide by log 3. It doesn't. You can, but it doesn't work out as well as distributing. So what you want to do is you want to distribute. You want to distribute. So that's 7x log x plus log 3 plus log 3. Okay, so 7x log 3 plus, and then 1 times log 3 is log 3. On the right-hand side, you have distribute this in. So that's x log 7 minus 3 log 7, right there. Okay, now what you want to do is you want everything with x's on the left-hand side of the equation, everything without an x on the right-hand side. Okay, so you go over there, you go over there. So this log 3 comes over as a negative log 3. This x log 7 comes over as a negative x log 7, right there. Now, what you want to do is you want to factor this x out of everything. So factoring x out of here, you get 7 log 3, and here you get minus log 7. And then you want to divide by that. Okay, so that's going to go over there. So x equals, and then the numerator is negative 3 log 7 minus log 3. And the denominator is this right here, 7 log 3 minus log 7. Okay, so that's the answer to the first part. And they also wanted you to do an approximation, boo. Okay, so we'll just put that expression into GeoGebra. I'm going to type the backslash key first, and then I've got a fraction run. So I've got a fraction running right here. So in the numerator was negative 3 log 7. Put that in parentheses minus log 3. Use the arrow key to get the denominator. 7 log 3 minus log of 7. And hit enter there. And I have negative, so 6 decimal places again. Negative 1.207501. This 1 gets raised to a 2, so 502. Negative 1.207502. Okay, great. Okay, so now we have logarithmic equations. And here, again, what you want to do is combine into and isolate the logarithms. So here we have a sum of 2 logarithms. That's not good. But we can combine these together into 1 logarithm. Which is the product of this and this. Here we have this 2 that's not good, but this 2 can go up here. Like that. I don't know what happened. Can you guys hear me now?
Yeah, we can hear you.
Yeah.
Okay. Okay, so something weird happened on my end. I got muted, but I unmuted myself. So, let's see, where were we? Okay, so you could just do that, or you could just like exponentiate both sides. The e is the inverse of that, and we know that e to the log of whatever expression you have here is just x. So e to that is just 6x minus 9, and that's just x squared. Okay, so at any rate, you end up with that. Let me rewrite it like this, just so that I have this x squared over here leading out. So bring these things over here. Minus 6x plus 9 equals 0. And this factors into x minus 3 and x minus 3. Okay, so that's going to give you x equals 3 as the answer. Okay, now I did say you need to check the answers. Okay, when you're solving logarithmic equations, you need to plug this into the original. But it turns out this time we didn't do anything that would mess it up. Okay. We didn't do anything that would give us a wrong answer. So I'm just going to let it go this time. Okay, because this is always positive, and then so if you plug a 3 into here, then that's positive as well. So everything's fine. Actually, you know what? We should check it. We should check it with the original, because things could have gone wrong here by bringing this 2 up here. Now that I think about it, yeah, things could have gone very wrong there. So let's check it. Okay, so this is log 3 minus 3 halves is 3 halves plus log 6, and then the right hand side is 2 log 3. That's the same as, but that's the same as this 2 can definitely go up here, so that's log 9. And this one right here, these can combine to 3 halves times 6. And that's log 9 when you multiply this together. So that checked out. So that works. Okay, let's do number 9. So this is log base 10. Now this is isolated, and that's isolated too. So if you take 10 and raise it to both sides, okay, so here's the left-hand side right there. Here's the right-hand side. They're both, it's 10 raised to each side. Then right here, we're using the property that 10 raised to the log of x is just x. Okay, so all this is just going to give you 5x plus 3. And 10 to the 1 is just 10. Okay, so now the 3 can go over here. So subtract 3 from both sides, that's 7, and divide by 5, so that's 7 over 5. Okay, so it's that. Okay, now let's go to the next one. Okay, so log base 21 of x minus 3 plus log base 21 of x plus 3 equals 1. So we're going to combine those together. Since it's plus, then it's multiplied inside. Equals 1, and that's just 1 right there. Okay, so let's multiply everything together. So that's x squared, the first one. The outside one is x minus 3x, that's minus 2x. And then the last one is minus 3. Yeah. Okay, so now what we're going to do is we're going to exponentiate. We'll start with 21 equals 21. We will raise the left-hand side to this one. We'll take 21 and raise it to the left-hand side. And 21 raised to the right-hand side. All that goes away. We just have x squared minus 2x minus 3 equals, and this 21 to the 1 is just 21. Okay, now subtract 21 from both sides. You have minus 24. We can factor this into minus 6 and plus 4. Okay, so this gives you 6, this gives you negative 4. Okay, if we plug a 6 in first, so plug in x equals 6. So you have left-hand side and right-hand side. Okay, 6 gives you log base 21 of 6 minus 3 plus log base 21 of 6 plus 1. The right-hand side is just going to be 1. Okay, so this is log base 21 of 3 plus log base 21 of 7. Those ones can combine 3 times 7, which is log base 21 of 21. And that's equal to 1. So that checks out. So this works. So 6 works. Now we check negative 4. Again, the right-hand side is just 1. And the left-hand side will be log base 21 of negative 4 minus 3. Log base 21 of negative 4 plus 1. Okay, so this is log base 21 of negative 7. Log base 21 of negative 3. And this one is wrong. You can't take logs of negative numbers. Okay, so that's you have to throw that one out, and the only answer is 6. Okay, now, so what happened? Why did this give us this answer? Well, if you pretend that we can do the combining, we can do this step right here and combine these together, then that's going to be log base 21 of negative 7 times negative 3. Negative 7 times negative 3 is positive 21. So you can take the logarithm of a positive 21. You just can't take the logarithm of these two. Okay, so this original equation, so this negative 4 does not work in the original equation. Okay, let's look at number 11. Find the time. So here we're talking about compound interest again. Find the time required for an investment of $4,000 to go to $8,000 at an interest rate of 6.5% per year, compounded quarterly. Okay, so this means that n is going to be 4 right here. So n is going to be 4 in this formula, and we're going to use this formula for number 11. Okay. So you want it to go from, so this right here is our amount that it's growing to. This is our principal, and the rate is going to be 0.065. And we want to find what t is. So plug everything in. So $8,000, we're plugging that in there. And then $4,000 for p. And then 1 plus 0.065 over 4 to the nt. So that's 4 times t. Okay, great. Now, we can cancel those with that, and then 8 divided by 4 is 2, so that's 2 equals 1 plus 0.065 over 4 to the 4t. So what you want to do now is take the natural log of both sides. It's just solving an exponential equation. This is going to go out in front. This is going to go down in front. Let me switch sides. Let me put this on the left and then this on the right, okay? Okay, so you have this t right here. We'll take the 4 and all this logarithm and we'll divide both sides by that. And that gives us this. Like that. Okay, now they want us to answer to 2 decimal places. So we will we'll go to GeoGebra and have it do that. Wait, what did I just do? Okay, okay, so GeoGebra's turn. Okay, let's see here. Okay, so we have the numerator was log of 2, and the denominator was 4 times the natural log of 1 plus 0.065 divided by 4. Okay, so 10.75 years was the answer. That's approximately 10.75 years. Okay, great. Let's look at number 12. Here we're compounded continuously, so that means we're going to be using this formula here. How long will it take an investment of 2,000? So that's our P, is 2,000, to double in value, So that means that A is going to be 4,000. Okay, because if you double 2,000, you get 4,000. And the rate is 0.065. Okay, so let's set everything up. So we have A equals P e to the RT. So we'll plug in 4,000 for A and 2,000 for P. And the rate is 0.065. Okay. Okay, so now we divide by both sides by 2,000, and that gives us this. Let me rewrite it like this. Let me write it as e to, oh, this is a t. Oops, sorry about that. I forgot, I put the r but not the t. That's t. So e to the 0.065 t equals 2. So now we take the natural logarithm of both sides. And all of this just becomes 0.065t. So t is the natural log of 2 divided by 0.065. Okay, so let's use GeoGebra to figure out what that is. So log 2 divided by 0.065, and it's 10.66 years, 10.66.